Welcome to the deep dive. We sift through the sources to bring you the core insights. Today, we're really getting into the work of Christiaan Huygens, a real giant from the 17th century, Dutch polymath, right? Physicist, astronomer, inventor. He did so much. Most people probably know him for the pendulum clock, maybe Saturn's rings.
Definitely those. And the wave theory of light, his ideas on centrifugal force, oscillation, foundational stuff. But what's really fascinating looking back through the sources is this sort of underlying theme. He didn't just observe things moving. He seemed to get, almost intuitively, that motion is rhythm. That rhythm is reality, in a way.
Motion is rhythm, like an early sync theorist. Is that what the sources suggest?
Exactly. He was seeing how motion systems, stabilize themselves through rhythm long before we had, formal motion theory.
Okay, that's a really interesting angle. So before we jump into his big inventions, maybe quickly explain motion theory itself. Why is it so useful for understanding Huygens?
Good question. So motion theory basically suggests the universe isn't just static objects getting pushed around by forces. Instead, it's all about motion loops. These repeating patterns of movement, think orbits, cycles, oscillations, and these loops naturally try to find rhythm, to synchronize with each other. Stability comes from movement itself, like everything's sort of dancing together.
Dancing to an invisible beat. I like that.
Yeah. And Huygens, well, he seemed to just get this, even without the modern terms. So our mission today is to see how his specific discoveries actually show this understanding.
Right, how they reveal this motion as rhythm idea way back then.
Exactly. Centuries before the theory was formalized.
Okay, let's start with the big one. The pendulum clock, 1656. The first really accurate way to keep time. It's hard to overstate the impact, right? Before that, navigation, science, timekeeping was just messy.
Totally messy. His clock changed everything. Precision became possible.
And it comes down to what he understood about the pendulum itself. Isochronism.
Isochronism, yes. The idea that the swing time, the period, is constant, regardless of how wide the swing is, within limits.
Okay.
And from that motion theory perspective, it's just beautiful. A pendulum is a perfect looped motion system. It's stabilizing itself under a gravitational constraint. It finds this perfect rhythm, this sync state.
Okay, looped motion system, gravitational constraint. Can you simplify that a bit?
Sure. A looped motion system is just any movement that repeats, a swing, an orbit, anything cyclical. And gravitational constraint just means gravity, the main thing shaping that loop, always pulling it back.
Right.
But the key thing Huygens saw, maybe without saying it in these exact words, was that gravity wasn't just pulling. It was setting a tempo, like a metronome.
Ah, setting a tempo.
Yeah. So the pendulum isn't just counting seconds. It's resolving motion. It's tuning itself into the natural rhythm of falling, the rhythm gravity imposes.
Wow. Okay, so it's not just a clock. It's like a physical demonstration of motion finding its own rhythm. That's a big shift.
It really is.
And that leads right into something even weirder he noticed, this odd kind of sympathy. He found that two pendulum clocks, if you put them on the same wooden beam, they'd eventually start ticking exactly opposite each other, perfectly out of phase, but synchronized, even if they started randomly.
Yes. Wild, isn't it? How are they talking to each other?
That's the question.
Well, motion theory sees this as motion loops phase locking through a shared constraint. It's not like one clock is physically pushing the other. It's more subtle. They're interacting through the tiny vibrations, the shared tension in the medium, in this case, the beam they're both attached to.
Okay, shared tension, like feeling the vibrations through the floor if someone's tapping their foot.
Exactly like that. It's what we now call motion entrainment. The loops adjust, they resolve the forces between them until they find a stable, shared rhythm.
Entrainment, like fireflies blinking together.
Precisely. Or heart cells beating in unison. We see it in biology all the time now.
Yeah.
But what's so cool is Huygens saw it mechanically first. He had this physical, observable proof of sync happening.
That's incredible. Did he just stumble upon this, or was he looking for it?
Well, the story goes he first noticed it somewhat by chance with clocks in his room. But then, being Huygens, he got curious. He deliberately set up experiments, mounted clocks on the same beam, maybe tried different beams.
Yeah.
He studied this sympathy.
So he was actively investigating the rhythm, the connection.
Absolutely. Which brings us to maybe his most radical idea for the time, light.
Ah, the wave theory. Newton was all about particles, right? Corpuscles.
Exactly. Newton saw light as tiny bullets. But Huygens, in 1678, proposed something completely different. Light is a wave motion.
How did he picture that working?
Well, his core idea, which we still use, is Huygens' principle. Every point on a wavefront acts like a tiny source, sending out new little wavelets.
Okay.
And these wavelets combine to form the next wavefront. He showed how light spreads out spherically and how reflection and refraction worked perfectly if you treated light as waves bending and bouncing, not particles colliding.
So how does motion theory see this? Not just waves, but...
Right. For motion theory, light isn't really a thing moving through space. It's more like a pattern of structured motion propagating through what we now call a sync field.
A sync field? Okay, need a bit more on that.
Think of it like ripples on a pond again.
Yeah.
The water itself doesn't travel across the pond, right?
Yeah, it just moves up and down.
Exactly. But the pattern, the waves, travels across. The sync field is like the medium that carries that pattern, that rhythmic influence. So where Newton saw billiard balls, Huygens saw these oscillating loops of motion spreading outwards.
Oscillating loops.
Now, he did believe in the ethers, some invisible substance filling space for the waves to travel in. We know that's not quite right now. But his fundamental insight that light is a rhythmic transfer of motion, that was revolutionary.
And motion theory would say vision itself isn't detecting particles hitting your eye.
Exactly. It's detecting resolved sync. It's your eye system synchronizing with the incoming light pattern, the incoming rhythm. Huygens saw light is motion. The next step, which he didn't quite take, is seeing that everything is motion.
That definitely changes how you think about just seeing things. Okay, so he applied this rhythmic thinking to forces too. Centrifugal force.
He did. He defined it that outward pull you feel when something moves in a curve. And he even worked out the math. F equals mv squared over r.
Which is still what we use.
Yep. But again, look at it through the sync lens. Motion theory doesn't see centrifugal force as a real force pushing outwards. It's more like the structured motion loops resisting forced resync.
Resisting forced resync.
Yeah, when you force something that's moving nicely in a straight line or stable loop into a curve, you're messing with its pattern. You create phase distortion.
Phase distortion, like making it wobble.
Kind of, yeah. Imagine that spinning top again.
Yeah.
Nice and stable. Then you try to force it into a tighter curve. It resists, it pushes back. That feeling is centrifugal force.
Okay.
The phase distortion is that wobble, that instability, as the loop tries to keep its preferred rhythm while being forced into a new shape.
So it's the loop trying to maintain its own internal rhythm against the curve.
You got it. It's the tension between the loop's natural way of resolving motion and the external constraint forcing it to curve. That's sync physics right there.
He was seeing these patterns everywhere. Clocks, light, forces. Even astronomy, right? Saturn's rings tighten.
Yes, and significantly, he didn't see the solar system as just static clockwork gears. He saw interlocking systems of curved motion loops. His work figuring out Saturn's rings actually involved modeling how light would reflect off them, which shows, again, he's thinking of light as a looped propagation, not just a one-way beam hitting something.
So it wasn't just planets moving, but planets interacting through these loops of motion and light.
That's the implication. It's one of the first real attempts to map out these recursive systems influencing each other through their motion and the light connecting them, seeing the universe as this grand, interconnected rhythmic dance.
Okay, so let's pull this all together. Huygens' legacy.
Well, like we said, he didn't explicitly state everything is motion. But pretty much everything he studied was about motion and its inherent rhythm. Pendulums swinging, clocks syncing, light waving, planets orbiting. He kept finding this invisible rhythm structure under the surface of reality.
So motion theory looks back at him as maybe the first great observer of synchronization.
I think that's fair. He wasn't just measuring how things moved. He was watching motion resolve itself, watching it lock, align, phase, find its rhythm.
He thought he was building better clocks.
But he was actually discovering the clockwork of motion itself, the fundamental beat of the universe.
A really profound way to look at his work. He saw the universe as dynamic, interconnected rhythms way ahead of his time. So for everyone listening, maybe think about this. Where else might this idea apply? Motion resolving through rhythm, systems syncing up, things you might see as static or separate. Could there be an underlying clockwork of motion there too that we just haven't recognized yet? Something to think about.